So we still have another law left that's called ideal gas law, but it's a little bit different from the ones we've been doing. So we're on Avogadro's principle, or Avogadro's gas law. And it states that whenever you have equal volumes of gases at the same temperature and pressure, then they will contain an equal number of molecules. The volume and the number of moles are directly proportional or directly related. So if I have a certain volume and it can be a couple of different gases, if I was able to count those particles, they would be the same. They would probably have a different mass because each particle would have a different mass, but as far as the number, that would be the same. So our formula for this is V1N2, which is equal to V2 over N1, not over, times N1. And N is equal to moles. MOL is the abbreviation. It has to be in moles, not in grams. If it's in grams, then you would have to use your molar mass to convert it. So this one says if 2.3 moles of a gas occupy a volume of 73 liters, so that's my N1 and my V1, how many moles would be required to fill a volume of 126 liters? So that's V2, and what I'm trying to find is my N2. So we just start plugging in on our formula. V1 is 73 liters. N2 is my unknown. V2 is 126 liters. And N1 is my 2.30 moles. I need to get my N2 by itself, so that means I'm going to need to divide each side by 73 liters. So that's what should go in your calculator. 126 times 2.30 divided by 73. And I think the 73 is going to be the least amount of Sig Figs, so your answer should only have 2 Sig Figs. So what did we get on that one? Yes, sir. 4.0, and what would be my units? Moles, perfect. 4.0 moles. All right. And you have practice on that one. Like I said, pretty similar. Dalton's is a little bit different because you're adding up different things instead of it being multiplication or division. So Dalton says the law states that equal amounts of gas at the same temperature and volume have equal pressures. So if that's true, if I wanted to get the total pressure, and if I mixed several different containers together into one larger container and I knew the pressure of each one, I could just add that all up to get my total pressure. So the formula is P total, pressure total, is equal to P1 plus P2 plus P3, and you would just continue that for as many gases as you had that made up that P total. So if I had this container and I had one container that had gas in it and the pressure was 2 atmospheres, another container, same size, and it was 1 atmosphere, and then the third one, gas in it that was 3 atmospheres. If I put all of these together and put them into a container that was about the same size to get the total pressure, I would just simply add up how much individual was. So 2 plus 1 would be 3, plus another 3 would give me 6 atmospheres as my P total in that one when I mixed it all together. So kind of the only thing that can get a little tricky about this is Sig Figs, because whenever you add or subtract, remember that it is places behind the decimal, not the number of Sig Figs. So you have to kind of be careful with that. So we'll look at a couple here. It says, what is the total pressure in a balloon filled if the pressure of the oxygen is 170 millimeters mercury and the pressure of the nitrogen is 620 millimeters of mercury? So P total, my total pressure is just going to be when I add those two together. And since they're both in the same unit, since they're both in millimeters of mercury, I can simply add them together. So 170 millimeters of mercury plus for my nitrogen, 620 millimeters of mercury. So when I add those together, I'll get my total pressure. $790, and then our units are millimeters of mercury. Notice that neither 170 or 620 had any places behind the decimal, so that's why my answer wouldn't have no places behind the decimal also. All right, and then the next one is another way sometimes you'll see these problems. Instead of trying to figure up the P total, you're given the P total and you're trying to figure another gas. So now we have a second balloon, and now we know the total pressure. So that's my P total. What is the pressure of the oxygen if the pressure of the nitrogen is 720 millimeters of mercury? Well, one thing that I notice here, I have 1 in millimeters of mercury and 1 in atmospheres. And I can't add or subtract those when they're in different units. So the first thing that I'm going to do is I'm just going to convert one. So I'm going to convert my 720 millimeters of mercury to atmospheres. You could have gone the other way. You could have converted that 1.3 atmospheres to millimeters of mercury. So we've done this with our conversions. So 720 divided by 760 gives me 0.95 atm. And that is the pressure of my nitrogen. So now we got the same unit, so now we can solve our problem. Our P total, which was given to us, is equal to the pressure of our oxygen plus the pressure of our nitrogen, which was given to us, 0.95 atm. So to solve for the presence of my pressure of my oxygen, I'm going to bring my 9.5 over, so I have 1.3 minus 9.95, I'm sorry. You have to recognize at this point when you're doing your subtraction, this only has one place behind the decimal. That has two places behind my decimal, and I always go with my least. So my answer can only be one place behind the decimal. So although you get that in your calculator, 0.35 atms, you would have to, yes, sir, and get your point perfect. And that would be your answer. So that one is definitely different than what we've been doing. And both of those are on your pink sheet. If you want to mark them on there. Ronnie, can I erase this? Are you okay? Do you have what you need? Okay. If you look at your pink sheet, let's see if we can look. All right, reference sheet. So it's on the same side that we marked Boyle's and Charles's. So under behavior gases, if you see the very first one is Dalton's. I don't know where you want to mark it, here or here, but anyway, that's your Dalton's, where you're adding everything up. And then what other one did we do today? Avogadro's, which is down here. Hold on one second. So I'm going to take it out of my fraction. V1 in 2 is equal to V2 in 1. Ideal gas law is completely different. And then this one, we didn't do one exactly like this. Closest we did to that one was our combined gas law. We just didn't put the moles in with it. All right, so on the next page, you see kind of a chart looking, and we're going to fill that out. Just a nice way to organize all of your different stuff. Maybe the only class I've been able to get through on this one. And you may choose to use this instead of your pink sheet. This may be easier for you to have all your things that you need. Gas laws. All righty, finally. All right. So let's just kind of do a summary. We should be able to get this whole page filled out. So for Boyle's law, we're looking at pressure and volume. And temperature is being held constant. This is an indirect or inverse relationship. It's the only one that we have that's not direct. So a graph would look like this. So inverse. So my formula is P1 V1 is equal to P2 V2. And then next was Charles's, where we looked at volume and temperature. So pressure was held constant. It's a direct relationship, so its graph looks like that. In fact, that's all the rest of the ones that we're going to talk about are direct relationships. So this is direct. V1 T2 is equal to V2 T1. Then Gay-Lussac, we looked at pressure and temperature. So my volume was held constant. It's also a direct relationship, so it looks like that. And then we had P1 T2 is equal to P2 T1. And then today we did Avogadro's with volume and number of moles. So we held our temperature and our pressure constant. Still direct relationship. So my formula is V1 in 2 is equal to V2 in 1. Combined gas law looks at everything except the number of moles. So pressure, temperature, and volume are all part of it. That's too many variables where you can't just say how they're related, because if I change one, that's going to change that relationship. So we're going to skip all the way down here to the formula. P1 V1 T2 is equal to P2 B2 T1. So that's the summary of all those that we've done so far. So we're going to look at our four variables. The pressure is represented by P. We know units can be ATM, millimeters of mercury, torr, kilopascals, APA. I didn't have to write that all the way out. So our conversions, these are straight off your pink sheet. This is the same line that's on your pink sheet. 1 ATM is equal to 760 torr, or 760 millimeters of mercury, or 101.3 kilopascals. So those are all the things that we just used to do the pressure conversions. Volume is represented by V. Liters are probably the most common unit for gas. Sometimes you may see milliliters, centimeters cubed, or meters cubed. They're all possibilities, but it tends to be liters. All right, move this up a little bit for the last couple of ones. So we were at temperature. Temperature is represented by a T, and our units are Kelvin. And to get to Celsius, we just take our degrees Celsius and add 273. And that will get us to Kelvin. And then our number of moles is represented with a little n. Moles, or MOL for the abbreviation. The molar mass is used to convert between grams and moles. And something we haven't used yet is called the molar, MOLAR, volume. And its value is 22.4 liters per 1 mole. That's used to convert between volume and moles at STP. And like I said, we haven't done that yet. We'll do that whenever we do gas stoichiometry. But we have done this before. So if you were trying to use Avogadro's law, and instead of giving the moles of a gas, you were given the grams of a gas, then you would take your grams that you were given and divide it by the molar mass of the gas per 1 mole. And that would give you how many moles you had. Whoops. And then you'd be able to put it into your formula. All right, that was not quite perfect timing, but almost perfect timing. Okay, don't forget, tomorrow you have your stoichiometry retest, so please be prepared for that. And I will see y'all tomorrow. Grab a wipe, please, on your way, and wipe up real quick.